So for your next ungraded homework, there is a confusion. So what I expect you to do is, for these kinds of stencils, you take the value of E1 that is given here and just try to ensure that the other coefficients are following according to that reduced accuracy that is expected from the scheme, reduced Taylor accuracy. Okay. So some of you have tried to calculate the A1 by optimization. That was not the intention. If you have done that, great. But I was expecting you to use what you derive in terms of your relations between the various coefficients that agree with the reduced Taylor accuracy that is mandated from this stencil. So it says, now regarding boundary conditions, and since we haven't talked about source modeling, what if we have multiple sources? So do we have to add up the individual boundary conditions? So what should I answer to this?
This most likely would be a wrong answer, but the way I see it, like the boundary condition, it's not inherently like linked to the source. So we can use the same boundary condition with multiple sources. After all, it's a condition rather than explicitly a property due to the source.
Exactly. So it's the perfect answer. So what we are saying is that the source can be here, and this would be considered far enough away from the source that we can apply that boundary condition. That is, we can assume that there is some function r by v theta minus t theta by r to the power half, and so on. So suppose your pressure is like that. So you can assume this for this source, but you can also assume the same form for this source, because you are anyway making some approximations in that assumption. So remember, there is an order r to the power minus 3 by 2 here, and so all that is already assumed. So there is nothing further wrong that you can do by applying the same boundary condition for any source, and anyway you don't know the f, so you cannot do anything better. No, we did not. We chose the domain to be far enough away from the sources. That's it. If you have got multiple sources, you will try to set the origin to be the centroid of the sources. Nothing better that you can do. So that is the overall idea.
In that respect, since we're at far field, the angle won't actually change appreciably much also. So we can use that assumption.
Yes, everywhere. So but no, the v theta is changing, okay, because theta is different. So again, you have to assume that theta is with respect to the origin of your chosen boundary coordinate system, and so what you have as a theta here will be very different from what you have as a theta here, and you have to find out the v theta with that formula that is given.
Right, but what I meant to say was, like, if we take this center at like each of the points, since they're like very close together compared to far field,
Exactly.
switching angle, the angle does not change.
Yeah, so that's why this angle is only with respect to the origin that you chose. Hopefully intelligently that origin is placed in the vicinity of the sources relative to the far field boundary. That is, all these are close enough to this relative to the how far the boundary is to this point. That's all that we are saying. So we were talking about this Helmholtz equation. So we took the governing equation in for a quiescent medium for the sound waves, and then we started looking at how do each frequency of the solution behave, and we figured out that it subscribes to this Helmholtz equation, that for a given frequency the pressure fluctuation. So what is p hat really? For a given frequency, what do we mean by p hat? Amplitude, but it's a complex amplitude, right? So remember that our pressure, so we are saying that p at essentially what we are saying is that p at x comma t is the real part which we never state as much. That's what we are saying, right? So this is the amplitude, and it's complex in general, and this is the time behavior. Okay, so that is what we mean by that p hat, and that is governed by this Helmholtz equation, where the omega appears in the operator to the of p hat also, and the Laplacian of course is appearing. Next, what we are going to do is we are going to consider a very specific form of the solution, namely that p hat x and omega is some a times e to the power I. So just notice that if you recall what my p is, what we are saying is that p of x comma t is a of e to the power I omega t minus kappa dot x, and I again drop the real part. So what we are saying here is that because it's a linear problem, we are within our legal limits to look at each frequency separately, right? And so at that particular, so for a particular consideration, we'll think that the pressure is composed solely of this particular omega. That's why we don't have an integral over all omega. Okay, we are not doing that. We are not doing that because we are assuming that that is the only part of the solution that is non-trivial, or the other parts are all trivial for the moment. And again, that is allowed because they all live in their own separate houses. Okay, they don't talk to each other, the various frequencies. So now we are saying that this p hat is of this particular form where this a is a constant. So a belongs to complex domain, of course, but it's a constant. So you will recognize this form, of course, from your previous analysis of a plane wave. Remember, we looked at harmonic solution of plane wave. So there we had kappa x. Now because we are just doing this in 3D, now we have to be a bit more general, but not too much general, and we consider kappa dot x, where kappa and x are now vectors. Okay. So we will just now go and show you, and maybe it's clear to you that this is a plane wave. Okay, maybe it is completely clear to you, but let's just make sure that we all agree that this is a plane wave solution of quiescent medium Helmholtz equation. And we are proposing that as p hat x omega is a e to the power I minus I kappa dot x. So how do we see that there is a plane wave? So first, of course, we have to satisfy that does this satisfy the governing equation? So our governing equation for the Helmholtz problem is this one: omega square by c naught square plus del square of p hat x omega equal to 0. So does it satisfy the governing equation?
Because instead of having simply one frequency, we basically have to satisfy omega square by c square plus kappa x square plus kappa y square plus kappa z square is equal to 0.
So that's
Sorry, minus because of the I.
Right. Yes, exactly. We will have the same form of the dispersion relation as we had earlier. So what do we see? So first of all, to make it simpler, Einstein summation convention. Who doesn't know? You had raised your hand. Okay. So we'll do that a bit, so that because we are going to use this later. So let's just So let's just think of things in 2D first, and then we'll extend to 3D. So suppose you have got a 2D world, okay, there's nothing in the third dimension, our physics is all 2D. Then it turns out that our governing equations have got terms like this. For example, the mass equation is del rho del t plus u naught del rho del x plus v naught del rho del y, or let's keep it, okay, we can have this is equal to 0. And then you have got, say, del u del t plus u naught del u del x plus del p del x 1 by rho naught equal to 0, um, del u del v del t. So I'm just writing the Euler equations that you should be very familiar with. del V del X plus V naught. Oh, I don't. So these are the forms of equations that you encounter not only in Navier-Stokes but in all of physics. There are equations that look very much like this. And our equation in terms of pressure for the energy equation was something like this. So you will be deriving these things for your homework also, the next homework that I posted. Okay. So these are the sets of equations you will derive. So what was observed by this famous gentleman is that the terms that appear are generally of this form. For example, we have got the divergence of velocity as in here, which is del u del x plus del v del y. So to make things even clearer, what we are going to do is we are going to set now x 1 is x and x2 is y. Okay. So everywhere that there is x, I will call it x1. Everywhere there is y, I'll call it x2. I'm going to overwrite badly. Please pardon me. So all my that will bring out the pattern even more. That wherever I see y, I'll call it x2. Wherever I see x earlier, I'll call it x1. Okay. Just a new nomenclature for the coordinate system. So basically, we are saying that the coordinate system is x1 e1 hat plus x2 e2 hat, where e1 and e2 are the Euclidean unit vectors. So then this becomes even clear that and okay, of course, that your u vector is u1 e1 plus u2 e2. So then I'm going to replace my u01 u02 u01 u02 u1. Okay. So everywhere I have to do that u1 u2 u2 u01 u02 u2 and so. But then this form becomes very nice. So I've got the divergence as del u1 del x1 plus del u2 del x2, which I can write as summation del ui del xi, I is equal to 1 to 2. And if I had 3D, divergence of u will also be very similarly del ui del xi, I is equal to 1 to 3. If you have say 2D dot product, okay, that is there is one vector a and you are taking dot product with another vector, that again is a summation I is equal to 1 to 2 ai bi. 3D, we've got a dot b, now it is summation I equal to 1 to 3, otherwise it's the same. So noticing everywhere that whenever an index is repeated in an expression, that always is associated with a summation over that index. So this term has got del ui del xi. That means that that is always associated, when you can see the pattern here, that's always associated with a summation over I equal to 1 to 3 in case of 3D. In case of here again, there is a term, there is a product term where an index is repeated. So that is always going to be associated with a summation of I equal to 1 to 2. Here I equal to 1 to 3. For example, suppose you have got a term, so you will remember that our momentum equation in 3D looks like this. So this was the non-linear, so not linearized. So the original 1 by rho naught momentum equation in 3D. Okay. So then the ith element of this is a vector equation. So the ith element of that is del ui del t, that is, say I is equal to 1 is the x component of this. So what is this term? Abhinav, since you don't know, what is this term for the ith equation? What is this term? Uj. So that's the knowledge of that's the prior knowledge that he is using there. So what he is thinking of is there is u1 del u I del x1 plus u2 del u I del x2 plus u3 del u I del x3. Let's go and check whether this is the form. So there is a u1 del u1 del x1 plus u2 del u1 del x2. Here there is u1 del u2 del x1, u2 del u2 del x2. So this is the form, and because we have already used up I cannot use that I again. So I always is associated with this variable whose derivative is being taken. So I have to be bit more stingy with my I and instead write this as summation with some other dummy variable of integration, say j. J is equal to 1 to 3 uj del ui del xj. Okay, plus pressure term, no summation, this is just the ith equation. Ith equation is del p del xi 1 by rho naught del p del xi, that is equal to 0. That is the ith component of this momentum equation, the vector equation. Okay. So now again you see that there is a repeated index, this time j, it's just a dummy index, but the only thing that you have to keep careful about is that this I cannot be used for that, okay, because that's a I is already used up. So it's I is already accounted for. So now again Einstein came in and say that why write it when it is implied by all these things, that all these experiences telling me that whenever there is a repeated index in any product term, then that is going to be always associated with a summation over that repeated index from 1 to 2 or 1 to 3 depending on the dimensionality of the problem that we are dealing with. So instead of writing that summation repeatedly, I am going to just omit that summation, with that going to be implied. So there are notes about this in your, so notes about this you can look up in your notes for the 3D perturbation discussion. So there you will find it, okay. So now I am just going to use this to derive the Laplacian of the pressure. So just let's go with that. So I want to again remember that p hat x omega is a e to the power I kappa dot x, there is a minus, and so I'm asked to do del square p hat x omega. So Shujoy, how should I write this in Einstein convention? What should I write? Remember that del square of some scalar f is in Cartesian coordinates del 2f del x1 square plus del 2f del x2 square plus del 2f del x3 square. So how do I write it in terms of Einstein convention? Del xi del xi, just to make it clear that there is a repeated index of I. So this is del 2 p hat del xi del xi. So I will take one at a time. Del p del xi is a del xi of the exponent times e to the power minus I kappa dot x. So how should I write that exponent? So I should not use I because I is the complex square root. I'll use j instead of I. So what should I write? I kappa m xm. So I have stayed away from j. J is not allowed. I've stayed away from j. Here it doesn't matter. Here is in the vector form. So this is now What is this? Kappa?
Delta
Km. Del xm del xj is delta mj, Kronecker delta. Okay. So remember what we are doing is del xm del x j. So when m is equal to not j, then there is 0, right? These are independent orthogonal coordinate directions. So this is only equal to the Kronecker delta. So 1 when m is equal to j and 0 otherwise. Okay. So that is that. So kappa m delta mj is kj, because whenever m is equal to j, this is going to be 1 and I am going to pick that kappa j, and whenever m is not equal to j, then that guy will be always 0. So this becomes minus I kappa j a e to the power minus I kappa dot x. So then what is the del square p hat?
What if we take a non-orthogonal basis this time? Like the primary assumption we had was an orthogonal basis, which is why we got like the delta, and that simplifies down to this simple,
Yeah. So this is Einstein's summing convention is for Cartesian coordinates. So it is also called Cartesian tensor notation. To my knowledge, it works for Cartesian tensors only. What do you have? So we just apply it one more time. So what is being asked is that we have to do del xj again of del p hat del xj, right? So that was this guy. I should again replace this by g. So that will be basically del xj of minus I kappa j a e to the power minus I kappa dot x. So again, minus I kappa j is not a function of xj, so it can be taken out, and I again get the same problem as before. So that brings out another minus I kappa j. So this time whole square a e to the power minus I kappa dot x. So this, what is this quantity? What is that kappa j square? What is that? Magnitude of kappa. Just a kappa is just a vector. So magnitude of kappa square, right? You can think of it again as a dot product, square of the dot product. So I've got minus, because it's minus I square is minus 1, kappa j, and then this is just p hat. So this is just p hat again, and so this kappa j is kappa dot kappa, which is the magnitude of kappa square, which we are going to denote as kappa without the underline or any. So kappa is defined as root over kappa j is equal to norm of kappa vector whole square, just the magnitude square of the kappa vector. So till now we have not made much sense of that kappa vector. We will now start making sense of that kappa vector. So that's the entire exercise. But first we just showed that this del square p becomes this thing, and we have to satisfy Helmholtz equation. So now we check, can we satisfy? So we had omega square by c naught square plus del square p hat is omega square by c naught square minus kappa square p hat is equal to 0. So for any arbitrary p hat, this will only be satisfied if this quantity goes to 0. So we end up with the omega square equal to kappa square c naught square. So omega equal to plus minus kappa c naught, or if you trust omega more, then kappa is plus minus omega by c naught. Should look familiar to you. Why is it familiar to you? And plus minus solutions are the left and right running solutions, or in this case not just left, it can be this way and the other way. So what we are finding is that the magnitude of kappa has to be related to omega that you chose. So again, you chose the omega to consider, you chose the frequency to consider. For that, you are finding that this kappa in your claimed solution, where is my claimed solution? This claimed solution, the kappa cannot be arbitrary. The magnitude of kappa must be related to omega through the C naught, which is our dispersion relation that keeps coming back again and again. So this is the dispersion relation. And of course, it is for the plane wave, which we have already seen before. Now only we are allowing this plane wave to be in 3D domain, and it can be in any direction. It can go in any direction and not necessarily in the x direction. That's the only difference. There is nothing other. So that we'll see more clearly. Yeah, so norm, so the square of the norm is kappa square. So norm of a vector is the root of v1 plus v2 plus v3. So it's a magnitude. Okay. So let's now go back to make a bit more sense of this. This should already be very quite clear to all of you. But let's make more sense of this by remembering that in the time domain, that is in the physical time domain, our solution now looks like A e to the power I omega t minus kappa dot x, because there was a time factor which was e to the power I omega t that we assumed when we chose that particular frequency. And now we are seeing that the kappa is related in magnitude to plus minus omega by c naught. So now we say that let A be magnitude of A plus e to the power I some phi naught, where phi naught is the phase of that complex quantity A. So I just separate the magnitude and phase. So then we can write this as A times e to the power I omega t minus kappa dot x plus phi naught. So phi naught of course is the angle of A. So this argument of the complex exponential is the phase of the sinusoidal wave. So this is just elementary education again for you, because you know all that. I'm just trying to say that again. So that is what we mean by phase of the wave, right? Currently, what is the value of this exponent? So all these are real quantities, and so that will give me the phase. For example, when this is 0, that's a 0 phase. When this is 90 degree, that's a 90-degree phase, and so on. Or pi by 2 if you're favoring radians. So this kappa is the wave number vector. So we have seen the wave number scalar earlier in a planar wave in x direction. Now we are seeing the wave number vector. Okay. So why is it the same wave number? Because we can make the same connection with the wavelength again. So at any instant, the phase of the wave is constant on planes normal to kappa vector. So this is to be observed that this pxt is some solution, some field over the entire domain. I want to see at what all points is the phase the same. Okay. So I want to find out where all is the phase going, where all in the sense in what locations in x is the phase going to be the same. So I'm taking a snapshot of the field, that is this pressure field, taking a snapshot. So time is constant. So phi naught is also constant. So phase will be constant if kappa dot x is constant. So let's see here. So let kappa be this vector, okay, and this is your chosen origin. So this is 0, 0, 0, and this is a point whose position vector is x1. This is another point whose position vector is x2. Is the phase the same here at these 2 points? How do we find out? If kappa dot x1 is equal to kappa dot x2, because remember the phase capital phi is omega t minus kappa dot x plus phi naught, and we have set time to be constant because we are taking a snapshot. Phi naught is always constant, that's for the particular solution. So if kappa dot x is constant, the same at these 2 points, then I've got them at the same phase. How do we find out whether this is the same phase? So kappa dot x1 minus x2 is equal to 0 or not? That's the question to ask. So when would, so x1 minus x2 is x1 minus x2. So it is this vector is x1 minus x2. Is it orthogonal to kappa? That is the question. So that's the question. So whenever it is orthogonal, then these 2 points are going to be at the same phase. So all points such that this is 90 degrees will be all on the same phase. So that's a plane. It's a straight flat plane, and that is normal to the kappa direction. So this is a kappa direction and this is my plane. All points on this plane are at the same phase. That's a plane wave. It's obvious, right? So that's why we call it a plane wave solution. So you try to find a surface arbitrarily deformed for now that is normal to kappa. That's going to be a plane wave. Just like this guy. So that is what you find is a plane of or a surface of constant phase. So surface of constant phase is a wave front. You know all these things. That's the definition of wave front. What is wavelength? Childish questions. In the same way, or 2 pi. So we are trying to find out if this is a wave with phase phi at a particular time instant. At the same time instant, we are looking for another, it will be a plane, another phase which is another plane which is phi plus 2 pi. Then the shortest distance between them is going to be lambda, right? So it's a trivial exercise to find out that lambda indeed will be 2 pi by kappa or 2 pi by kappa. Okay, you can do that at home. So that's why this kappa is called the wave number. It's inverse of wavelength. It gives you a way of enumerating waves. So another concept is phase speed. So phase speed is time rate of motion of wave front normal to itself. So now we have to take 2 pictures. One picture now, another picture immediately after. And in that immediately after picture, my wave would have moved some distance normal to itself. Let's call it delta x. So this is at t is equal to 0 and this is at t is equal to delta t. So after some time instant, that same phase plane or wave front has moved some distance at delta x, and you can again figure out what that delta x will be for that delta t. Please find that out. So then take the limit. So you have to take the limit. So you'll find the Cp, that is the phase speed of the wave, as the limit of delta t tending to 0, delta x by delta t. That is a definition of velocity. Right? So what is that? Same phase. That's the idea. Phase is same. It will be seen, of course. What else can it be for a plane wave? Everything is so simple. So you just have to equate. So there is phi, which is say omega t plus minus kappa dot x plus phi naught, and I want to evaluate omega t plus delta t minus kappa dot x plus delta x naught is defined normal to the wavefront. So that normal direction is the kappa direction. That is the meaning of kappa. So this is delta x kappa hat, I can say. There is a unit vector on the kappa direction. So my delta x is not arbitrary direction, but the change in the x that I am looking for is delta x in the direction of the kappa vector. So it is the kappa unit vector. So if you do the cancellations, then we'll find that delta x is equal to omega delta t by kappa dot kappa hat. What is kappa dot kappa hat? That's the magnitude of kappa, projection of kappa onto itself, magnitude of kappa. So this is the omega delta t by kappa, which is C naught delta t, because of that relation between kappa and omega that we have established earlier. So your Cp is limit delta t tending to 0 of delta x by delta t, which is just C naught. So everything is very beautiful for a plane wave. Phase speed is equal to the speed of sound. It's not always true in all waves.